All right, welcome back. So next up, so far so good. You had taken any stat course?
Sir, I have done my MBA IT systems plus engineering also.
Okay, so in that way, okay, but you didn't. That looks like. But you are getting at least some idea what we are trying to say. Anyway, so let's coming back again to this so we applied this regression and replace the mean by the regression based estimate for the prediction. And now why it did better when we did the regression, why it did better? Anybody can explain?
Because it used all the data.
But really physically so it used the all data points, but mathematically, conceptually has been something happening. So what exactly the reason why it did better? So think about when I started with your mean, when you are using just the average, like you don't have any other auxiliary variable, auxiliary information, no other information, you are just using the average, and that's a very good estimate. That would be, it is generally lousy estimate, but that would be good estimate in one possibility. What was that possibility? Homogeneous. What does it mean? That means in all aspects it is homogeneous. That means its number of employee, if everywhere is exactly the same, that means this number of employee would not vary. That means everybody would clubbing to the one point, and everybody is clubbing to the one point, then you will have this average, and wherever you go, that means it doesn't depend on this information, doesn't have any additional information, because it just average all these things clubbing into this part, and for that you are calculating the mean of the total budget. So then when you are trying to predict on the mean number of employee for a new IIT, that is also going to belong into this region, because this does not exist. As I say, homogeneous means all IITs has the similar number of employees. That means everybody probably right here. So and when you are predicting the new one, that number of employee would be also here. That means the mean of the expenditure would be somewhere here. So in that case, mean would be the kind of the very good estimate. You really don't need to do anything. But in reality, that is not the case. We already kind of just looking this data. If you have 2, then the mean is somewhere here. If the number of employees 4, mean is somewhere here. All these things. So that what essentially it means, that the response variable mean, that means what we are trying to predict for like the total budget of the new facility, that this response variable mean that varies over the number of employees here. So what the regression is actually thinking, there are multiple means, not only one mean anymore. If you have a number of employee 2, then there is one mean. If the number of employee 4, then there is one mean. If number of employee 6, there is one mean. And what you are trying to think about, that means are actually linearly related. So not really the real variable, the mean of the response variable, they are related. And so what we are trying to basically capture the relationship of the mean, and then what we are trying to do, suppose the new IIT would be somewhere say 9 employee, then we are trying to predict for this 9 employee, if I had number of IITs which had the 9 employees, the expenditure would have been like varies, because even they have the same number of employees, but because of the different IITs, they will have different expenditure. But then we'll be predicting the mean of this part, and that's what we are trying to do by using this way. Instead of doing the grand mean, you are trying to mean whatever belongs to here in this case. So in other words, regression is thinking the mean of your response variable changes as the way your predictor variables changing. And you are trying to capture that varying mean by using the regression things. And mean, since mean follows this mean of the response variable follow the regression line. So if I can capture the regression line anywhere, I can predict this whole part. So that's why it worked better. Ideally, one could have done even better. If I had large number of observations here, I can actually fit a line for these things. I can fit a line for this. That means all IITs with employee 4, all IITs with employee number 6. So that could have been really ideal. But on the other hand, in this case also you get 4 data points. In many cases you have only 1 data point for these things. So as a result, you cannot fit the model. To fit the models, you need to have large number of data or minimal number of data. And what is the minimal number of data? By mathematics, you can do it 3, but the more data would be, the better result you will have, because there is a variance calculation. All these things, technicalities are there. So idea is that, but conceptually, had I have lot more data, so that's what another thing. So once the major data would come in, what we'll try to do, we'll try to build local models nearby. So that means, as I said already, we already thought about the regression means mean is changing for different value. So if I have locally huge number or sufficient number of data, we'll try to create some local regression type of thing. So which sometimes called the local regression, or sometimes we can think about even a general way non-parametric regression. So one of the concept I'm now trying to do, what would be calling as nearest neighbor regression. What does it mean? When I fit the regression, I won't use all the data point. If I am interested, say, predicting with new IIT which will have 9 employees, I'll try to make a model right here. That means I'll be using the data point only this area, this neighborhood area. I would not use the data from the other area. So this concept is called nearest neighbor concept, and if I develop the regression based on the nearest neighbor calculation, it is called the nearest neighbor regression. Everybody is clear what we are. So initially what we did, as you said, we used all the data, that's why it did better. But that may not do good. For example, if I go back to our previous example, if I go back to this example, if I use all the data, still your regression estimate would be bad, your prediction would be bad. You guys already said this thing, because this part is this way, this part is this way. But how about I just build this regression, I just take this set of points to make a small regression surface. I take this set of points, I do a regression. So that means it won't be a simple straight line, it could be a curved way. So essentially I'll be estimating some function f which will go smoothly through the neighborhood. It may not be going through exactly each point, but through the neighborhood, it will pass through the neighborhood. That is called the nearest neighborhood regression. Okay, very simple concept. But the concept of regression is still there, and then you will get the improvement. So if it is not a straight line, still you can apply the regression idea, but a little differently. So just let me introduce the very basic structure of the non-parametric regression, which called the nearest neighbor regression. So if the specified functional form in parametric regression far from the truth, just like example, our first data set, as I say, this simple parametric model means like this. Here you have the 2 parameters A and B. It is far from the truth for this second one. Then the prediction accuracy is our primary objective. A non-parametric method might be more preferable. So when I do these things, one thing is that our prediction would be good, but some of the other thing we might lost. For example, the explanatory power, many of the other mathematical power, all sorts of things, and also there are some variance, bias, trade-off, all sorts of things will come in. But nevertheless, you can make the prediction better. And that's why most of the machine learning target is that you try to make the prediction better. But oftentimes, you would lose lots of efficiency. And I'm going to talk a little bit about how the way you get there, you can lose the efficiency. Although your prediction is good, may not be it's a good idea to do that. But nevertheless, if it is not a straight line, you can still do this part. So there are several non-parametric methods. So Professor Dhar will do a little bit of basic non-parametric methods in this afternoon with more mathematical details. But you get the whole concept. As I said, that our first example, which we could not do using the linear regression, but we could do some kind of non-parametric regression for if our prediction is the goal. So k nearest neighbor is one of the simplest and best known non-parametric methods. That's what I'm going to tell you. Very basic concept. So suppose you are interested prediction in a new observation x0. That is like the new IIT, which will have the number of employee is x0. That's what you like to predict. What's the budget I need? But I do not know the exact relationship because the relationship was like this. So what I did, I thought that the relationship would be some f, but I don't know f. Then what you do, you define a neighborhood of that point where you are interested in, like we are interested in with the employee of 3000. So take the neighborhood with the 3000. How to define the neighborhood? That's again different question. It's a tuning parameter type of thing. But suppose you can define a neighborhood between say 3000 plus minus 500 employee. You define in this way. And take that values of y, just take the average. So k is the size of the neighborhood. How many neighbors you have in that local or n0 neighborhood. And you take this average. And that should be your prediction. So clearly here you are not using all the data points. You are using the data points only which are belonging to the neighborhood. In that way, what it happen, your estimated function will pass through much more close to the points, but it can have huge variability because you are not using all these data points. But nevertheless, in terms of the prediction, your prediction error might be much less. Okay, so very simple concept. It's a very practical way you can think about that. I'm interested in x0 value. Just think about the neighborhood of the x0 value, and you take this average, simple average. But there is other way also you can do, and then this is essentially called the k nearest neighbor. K means k is the size of the neighbor, and nearest means you are just taking with all the nearest part. All right, and many practical example you can find that it could be reasonable. But how does it look like? So when you do this way, then as I said, that your fitting will depend on what is the value of the k you are taking. Obviously, k equal to 1 means you are taking only one value. So for example, if I do, it may not be possible all the time, but the other example what I showed you, where is this other plot, second one here. If I go this one, no, sorry. If I go this one, then suppose I am interested in x0 value here, then I'll take this neighborhood only this one. So k equal to 1. You are not taking any other things. And in this case it is possible because you have number of values in that particular one. But I can take one left, one right as well. I can define this neighborhood. But there is some of the subjectivity is there, how the way you can define the neighborhood, etc. So what would be the impact? So you have to understand a little bit the impact, since this k is bringing another kind of the parameter you can think about, tuning parameter you can think about, because the previous one, what is our idea? Our idea was we'll have a line where the distance from each of the point for this line would be minimal. That's the way we chose. So that's our principle, and then we use the mathematics. But here idea is you have to find a k such that you will be happy, but what k would be, that's we don't know. So if you only I can do the plotting for a two-dimensional case. If you would like to take k equal to 1, then your plot would look like steps. In a two-dimensional one, how it should look like? If it is a linear regression, it's kind of a surface like this. So for example, like this is the surface in an increasing surface, right? But if I do the linear regression, exactly with a two variable, if I would have done this thing. But if I don't do the linear regression, if I just did non-parametric regression such as k nearest neighborhood, since this is the number of choice, how many neighbors you will be taking, then this might look at like very bumpy one. And this thing becomes smooth and smooth and smooth as the way you are increasing the k 1, 2, 3, 9. And it will exactly match to the linear regression if I take all the points, then it will match. Because that is the smooth possible, but then you are having a little bit more bias, because that other example, when you have like this, then if you fit a line like this will have more bias. But it is a very smooth curve in that sense. Straight line is the best or the smoothest one you can have. On the other hand, you can fit each point by point, as you said, actually you wanted to do that each point by point. This is also possible by doing this way, but then it would look like this. So what is the consequence of this part? The consequence of this part is that means this fitted curve, everything is estimated quantity. This one would have lot more variance. So when I'm doing the prediction, I might be very close, but my uncertainty of the prediction is very high. So the risk, in terms of the risk calculation, that could be much more riskier to do. It's always makes sense. You like to have much more accurate, then you are running with much more risk. But you kind of trade off, you can have little like biased, less accurate, then it is much more certain that you can do it. So in other words, you allow more error, you can do it. But if you think that no, I like to have this 100, then you may not get even 0. You cannot do anything. So these are the things always you have to keep in mind, that the bias variance trade-off is there. So the optimum value of k will depend on the bias variance trade-off. So somebody has to really understand how the way bias variance play. And when the parametric approach outperform non-parametric, when it does these things. So I'll try to display few of the plots like that, so that you can have some idea when a parametric approach would be preferable than a non-parametric approach, or a non-parametric approach could be preferable than a parametric approach. I do not like to say that always you do non-parametric or always you do the parametric, but in most practical purposes, oftentimes parametric approach is good because it is easy to understand and easy to explain. On the other hand, non-parametric approach might have difficult to explain, but for the prediction purposes, oftentimes it might be better, because the surface could be really non-parametric, and in that case it might be better. So let me just show you some empirical evidence, and then you will be the judge what to do. So here is the two plots. You can see the solid line, right? The solid line is the true relationship between two variables, x and y. One of the predictor variable, one is response variable. And then you can see that some blue line bumping around. That blue line, the left side, if you take k equal to 1, and the right one k equal to 9, you can see that these bumpy things little smaller than here. So that's the kind of the repetition of what I showed in a two-dimensional surface. Now it's become for the only one variables. So immediately you can see that bumpiness is lower. So that means your fitted curve would have less variability here than here. But here the points are going much more closer to the original points compared to this graph. So that means you are fitting data by data, but on the other hand you have very high variability. Here I'm not fitting just data by data because I'm averaging over the 9 data points, so it cannot go in the data by data, but it has the less variability. Okay? Same plot with this 64 observations. This one was k equals to 9, I think that was the fitting. Now what is this plot is the MSE. What is just I said that MSE is the mean square error, which is the bias plus the variance, or the square of the bias plus the variance. Okay, so it's the total variability it's measuring. So when you do the prediction, oftentimes what you do in a machine learning type of things, you have some data you use for fitting the model. Even here we did the existing data we used for fitting the model. Then when the new data we use, or some of the part of the data we used for the testing purposes, and then we can calculate the mean square error or the total variability from the test data set. If I do that thing, this one shows the mean square error, the total variability from the least square or the parametric fitting, and this one goes like this from the non-parametric fitting, what is the k nearest neighbor, and in the scale of 1 over k. So 1 over k means if k is big, then 1 over k is smallest, then the smallest possible MSE is possible. That means the highest possible values of k, as I said always or at the beginning, that if your k is large and large and large, it's going to be closer to the linear regression or the parametric regression, and that's essentially it is saying the same thing. But as 1 over k is bigger, that means k is smaller and smaller, it kind of goes up. So although in the previous plot you have seen that the k nearest neighbor or the non-parametric regression fitted the data very well or point by point, but behind the scene, which we usually don't show, that the MSE could be very high, and as a result your model may not have good validation. It may not, people may not use it. You can just take a experimental data and show that, oh, it is working well, but in reality when you try to replicate, since it has high variability, it may not fit exactly the same way, because sometimes it can go like this, sometimes it can go like this, sometimes it can go like this. Okay. So now that was the kind of in a real line, the situation was real line was a straight line. The true real line was a straight line. Now think about little bit more the true relationship is not really straight line, kind of curvy. This one is the true relationship. How does it work? This is the fitting, and this is again the total uncertainty comparisons. This line is from the least square fitting. That means still again you fit at a least square, parametric least square fitting, and this is the uncertainty measurement. And now you can see that uncertainty measurement due to your k nearest neighbor regression, that means non-parametric fitting, generally it is better when k is large, because 1 over k is small. That's still better, because initially it was not good, because the line true regression was exactly straight line. That's what it is. No way the non-parametric regression can be better than the parametric regression. When the relationship started deviating from the linearity like this, it started at least showing something betterness, but not really depending on again the value of the k. Immediate for some values, like if your k is not rightly chosen, how many neighbors should be, if it is not rightly chosen, your uncertainty can go very, very quickly to the up. And as I said that it is not easy to know how many neighbors you will have. Okay. So gradually what previous one and this one what is showing, if the true relationship is linear, then no way you can beat the parametric regression relationship. Some deviation you might have some hope, but there could be danger depending on the value of the choice of the k. Now go even a little bit more extreme. Definitely this is lot more nonlinear than this case, and under this case here is your parametric regression, what we just did in this morning, and if I do the k nearest neighbor, pretty much it's beating all the way. It's very much robust to the choice of the values of the k. So what does it read? It means that under simplistic situation, when we are talking about still one predictor variable, if the true relationship is kind of the linear, you should not do the nonparametric. If it is truly nonlinear, then possibly you should do the nonparametric if your prediction is the purpose. Okay, so you can get some guideline through these empirical studies. And these are the kind of the gray area, because since we don't have any good prescription for how to choose k, so you should be running a risk, because if your k is not suitably chosen, it can have higher uncertainty. But the whole picture is not that good if I go for make the problem more complicated. So this picture we showed when we have only one predictor variable, but in reality you will have more, right? Let's see if I try to do the same thing for the more predictor variables. So the p denotes the number of predictor variables. Here it is like 1, or I cannot read from here, reflection, 1, 2, 3, 4, 5 and 20. The first one for 1, second one is 2, third one 3, 4, 10 and 20. That means you are using 20 predictor variables, 10 predictor variables. Again I am comparing the uncertainty. That the green line is the nonparametric one, and blue is least square. It doesn't change because you are using all the data point. That's why least square is always fixed MSE. You are fitting y equal to a plus b x type of things. So how does it look like? When p equal to 1, kind of you are beating the, of course you assume that there is a the nonlinear relationship is there, then definitely my or k nearest neighbor is beating, because it is always below the line of this linear regression. If p equals to 2, number of predictor variable is 2, it's still good. P equal to 3 is comparable. P equal to 4, not too bad. Look at that, when you p equal to 10, p equal to 20, where it goes. It's way more than your parametric regression could be. So what is our lesson then? That if we do anything you do, you have to be very careful right at the beginning. If you can think about some good parametric model, just do it. If it is nonlinear, you should do the nonparametric, but you have to be very careful if you have large number of predictor variables. And it is, in general, it is true for the nonparametric regression. For the large number of predictor variables, it's very difficult to control. Okay, so generally nonparametric regression work well, or all the nonparametrics work well when we have large number of data, and when we are concentrating only 1 or 2 variables. Then it is easier. Even mathematically that is true as well, because too many things you have to control. Okay, so you got some idea about when you can do the nonparametric regression and when you do the parametric regression. And my personal recommendation is that if you can do the parametric regression, do that one first without any hesitation, and try to justify how your model is. So that's why I think, and other which I did not say at the beginning, that definitely the linear regression is a very simple approach for explaining the relationship between outcome and the features. Oftentimes it is a very simple approach for supervised learning. This is the very basic learning. Then for the prediction even. You will see that when I'll do the classification even, we'll start with the regression type of approach. And the linear regression can be thought of estimating simple mean more precisely, which we already proved that even empirically we proved that part. So there are a number of good things, and it is easy to understand the parameter has a good interpretation. All sorts of things are there, but nothing is free. So it can give you number of answers. Already I think I talked about that. Given a set of features, what response behavior should we predict, how good the model reflects the data already. But let me just touch base the last point. What does it mean? Given a set of features, what response variables should we predict? That means once we fit that data, are we ready to predict for any value? The answer is not. If you look at this plot, typically if you are fitting like in this region, you should, for a new value, if the new value is right here or right there, you should not predict. The prediction would be good, much better, if the new value, that x0, new feature variable x0, if it is closer to the mean of the existing data set. The best possible prediction can happen if the new point x0 is closer to the mean of the existing data set. And as you go away and away, you will have much more error in your predictions. And mathematically we can do this part. If I display all this formula, then you look at this formula very carefully, it will explain why this thing happened. Okay? So one has to be very careful where you are predicting. Like in a time series way, if you try to predict just for the next year, probably you have the best option. If you have to predict 5 years ahead, your prediction would be worst. If you like to predict 10 years ahead, your prediction would be even worst. Why? Because you are moving away from the mean very, very quickly. So if you try to predict, like when we are predicting the new IIT even, like what is the projected funding for the new IIT, if that new IIT's employee number is way different than the average employee number of these other IITs, then your prediction is going to be wrong. And that's also we have seen from this plot. But mathematically, actually, if you look at the formula for all these variance of this B, A, all the estimate, prediction variance, all these things, if you look at from there, we can explain this part. But I don't think I like to spend all this time on this regression, but it is explainable. So why I am saying this thing? If you have a linear regression, then all this thing would be easier to explain. But if you have a non-parametric regression, it would be difficult to explain. Why the variance is high, why it is I have so much error, it would be difficult. Okay? So some of the other consideration you should take into account whenever you are doing some linear regressions. If you have a qualitative predictors, you should be very careful how you are coding, because qualitative predictor means you have to do the coding, right? Like male, female, typically you do 1, 0, but why you will be doing 1, 0? Or say high income group, middle income group, low income group, how the will code? You can code 0, 1, 2, you can code -1, 0, 1, you can code 100, 200, 300. What you will do? Because how the will code, since it's an artificial, completely artifact, because there is nothing called the number, right? For a qualitative variables, you are giving the number. But what number you gives, that will change your result. So you have to know how to put that number. Okay? Then often if you have number of predictor variables, you assume some of the additiveness, like they are additive altogether, but in general they may not be. Okay, so if you have the outliers, like one of the value is far away from the others, it can kill your regression. Collinearity, if the predictor variables are highly correlated, that also can kill your regression fitting. So all these things you should keep in mind, but everything one should know details to learn the regressions. Otherwise, I think all these are important topic to learn the regression well, but definitely I'm not planning to cover everything. So by the end of this whole thing, may I ask you guys, now do you understand what is regression at least? And when, how, why it works, when it doesn't work? Yes. Right? You missed the best part in the morning. So, any question? So what we will do in the afternoon, probably you might do some of this, again play with R. It may be linear, may not be linear, but you try to explain why you are fitting this type of model. If you fit this type of model, then why you get this type of error? Why did you get a good result? But do some things in this afternoon we might do, okay? All right. So, if there is no other questions, possibly I can close this section. I don't think that this data we need to save anymore because we just created other data. Oops. So the next thing is,
in case of
yes, go ahead. Go ahead.
Non-parametric,
Ah.
and say more number of predictor variable, uncertainty will be very high.
For this non-parametric approach.
Is it because of the more correlation among the
No, the correlation among the variables that is also there for when you are doing the linear regression as well. But
KNN, is it because of the correlation when we have more number of predictor variables?
no. That's what I'm saying. It is not because of the correlation. It is just when you saw this one of the variable, as I said, that it can fit the data point well, but it's pretty bumpy, right? So now if you have more number of predictor variables, so for each of the, it's not exactly additive, for each of the cases this bumpiness would be there. So as a result, total variability will increase because you have to do for each of them, right? So general way, you may not see in any practical example where you are fitting non-parametric regression for more than 2 predictor variables, even 2 or 3 predictor variables in most cases, because it's not very realistic. Mathematically you can think about all this part, but it's not very realistic in that way. But we have other way. If it is a non-parametric type of things, we can make it everything parametric, which would be coming like high dimensional way we can think about. Everything I can make it parametric, and then I can fit this part. Still I'll be fitting non-parametric, but using a parametric model. So that's what I'm trying to say, that linear regression is so powerful. I can use the linear regression to fit a non-parametric regression completely. If I get some time, I might go even details, but let's see. But one of the high dimensional technique, that's what I will do it. But one of the application is that if you have a non-parametric model, you can write it in a high dimensional linear way, and then you have to solve this technique what I will be doing. Using the same technique you can apply. So although it looks like linear, but actually you are fitting a non-linear model. That's the beauty of the linear regression even. And then coupled with the high dimensional technique. The high dimensional technique, it would look like everything linear regression. That's beauty because you learned the linear regression well. So mathematically it looks like linear regression, but behind the scene actually you are working with a completely non-parametric regression. Okay, so what is the next thing is that the model selection. So what does it mean by the model selection? If you have only one predictor variables, then issue is only what kind of model I will see, and we talked about, you look at the data, from there you find out the trend, and then you take a parametric form, simplest parametric form equal to a plus bx. But it could be a plus bx plus cx square, it could be anything, but it still go by a linear way. Okay. So by the way, if you have a like Kirby type of things, what I could do, a plus bx plus cx square, like I can make a square term. But in terms of linear regression theory, this is still a linear model. As long as the coefficients are linear, it's a linear model. So mathematically it is a non-linear model because it has the square, but statistically it is a linear model. Okay? So the whole linear model theory goes. But so when you have the one predictor variable, then the model selection means, shall I take a plus bx or shall I take a plus bx plus cx square? Where do I stop? If you have, so this is the type of thing. If you have two variables, then things become a lot more complicated. Shall my model would be a plus, let me put b1x plus b2x, or b1x plus b2x plus b3x1 x2, because as you think about they could be related, plus b4x square cube. Where do I stop? If I have even, so what I said that if you have the one variable, okay, here is actually another example of a non-parametric model or a nonlinear model. How do you make it a parametric way? You all know that mathematically any nonlinear curve you can fit by a polynomial, right? Like a0 or a0 plus a1x plus a2x square plus a3x cube. This way you can go. So what is the mathematical rule? Your polynomial degree, if you make it high and high enough, it will be accurate enough. Idea wise, mathematics wise it is true, but now what I just said, still this is a linear model because the coefficient a0, a1, a2, these are all linear with respect to my response variables. So you can write down everything in terms of the linear model. So basically x square, you can create one variable x cube, you just give another name x3, x to the power 4, another name. So, but in terms of the model selection, so mathematics says that you take a high degree of the polynomial, but what is the high degree polynomial? Where do I stop? I can use the model selection criterion where to stop. So even for one, this is one of the things that for a non-parametric model selection, if you are modeling in a parametric way, it's a non-parametric but parametric model because it's a polynomial, but it's a linear model. So I'm using the linear model for the non-parametric regression, but I need a model selection. Where do I stop? So under linear model setup, very well set up criterions have already established and it works well. So what I'll do in this morning, I'll just touch base this few set of existing thing which works well under the linear setup. But note that already, as I said, even it's a nonlinear model, non-parametric model, if you parameterized by this way like polynomial, etc., you should be able to use some of these criterions to fit the model or to check whether or select the good model. Okay? So that's the purpose of doing the model selection. It's so general way, if I go the general structure, this is my response or the outcome variable, this is the feature vector or the predictor variables. General way you can think about the p dimension. Once again, this p is a generic notation. It need not has to be p different feature. If you are doing a polynomial, then essentially one feature, square, cube, all this way it comes, you just give different name. But where do I stop? Okay, so it's a generic way. Everybody is understanding that this is I can just call it a general p, but this may be all different feature vector, or it could be only one feature vector representing different derived variables. All right, or it could be like there are two variables x1 and x2. The first one is x1, second one is x2, third one is x1 times x2, fourth one is x1 square times x2, fifth one is anything. So that means you are capturing non-linear models as well. but in terms of the linear way. So that's what I have repeatedly I'm saying, that you need to understand the linear model very, very well. Then you can solve really large number of problems. So that's the feature variable. And in a regression or prediction objective, always what you have to do, we have to model y some function of the predictor variables, and always there is an error because we cannot capture the whole part. Like even if you are approximating a function, if you are doing a polynomial, mathematically polynomial degree has to go to infinity, then it exactly, but in reality it won't be. So there will be some approximation. So how much is the error? So all this error goes here. And in other realistic example, as we said, that when we are trying to improve our mean prediction, there are some of the controlled variables, some of the uncontrolled variables. So all uncontrolled variables would go here. That would be here. In a simplistic situation or the linear regression situations, we assume essentially this is the linearity on the parameters. So note that linearity on the parameters. Okay. At this point, you are thinking that this structure you know. But as I said, that oftentimes you are using this thing, known structure, but you are using to approximate an unknown function like a polynomial. But still I am writing in a linear way. Okay. And some cases, like maybe tomorrow or day after tomorrow, I might show you that exactly if a pure non-parametric functions also you can write in this way. Okay. But in any case, so that's why it is very important that to understand how it works in a linear model. So this is everything you write in a linear model. All right. So setup is the general setup. Eventually I bring it into a linear setup. So the existing thing, just to go quickly, let's take a small example, that the example we started with in the day 1. Yeah, a hospital surgical unit was interested in predicting the survival periods of the patients undergoing a particular type of liver operation. A random selection of 54 patients is available for model building. From each patient, record the following information was extracted from the preparation or pre-operation of the data. This is also available. I'll provide you this data in this afternoon. These are the 8 variables: blood clotting score, prognostic index, all this blah blah blah, all this part. Again, this is a very classic example. This part goes a lot more as a text, standard classroom type of lecture, because in reality nobody is going to tell you this is the data set I have, this is the problem, you have to think about what the data it would be. But generally this type of data being collected when the patient is in the hospital, this type of data is available. But there are many more data is available. So for the time being, suppose these things are available, and the doctor told you that these might be related to the survival period after that surgery. That's what you took this type of data. But what should be the model? Again, doctor thinks if they were sure that this is the variables related to that, they would not ask you to fit a model and do the prediction. They would have said, okay, these are the things I know very well. So idea is that out of this information, how many variables I can use, and what kind of, even if I use say 1, 2, 3, shall I use this way or square or cube, or there will be product or anything? How do I do the model selection? So what should be the right way to go? What should be the starting? Suppose this problem given to you, how the way you will do it? Unless I say that do a linear regression, how the way you will do it? So your objective is to, again, for prediction of the survival time after the surgery. And I gave you this much of data. How do you do that?
We'll have to find out the purity of the variable with respect to the target variable.
Fine. So how do you do that?
Maybe some entropy
Or first thing you might, so thing is that if you think that you like to predict this thing using some of the information, the first thing what you have learned, without doing anything, we could do that mean calculation, and mean could be the prediction. right? But our idea is to improve that from the mean prediction beyond the mean, use the mean. So we have to first think about there is a regression relationship or not, or there is an association or not. So what you should do, you should try to plot the data with all these things. But in true sense, how can you plot this? There are although 8, as I said, that 8 again given, we don't know how many are there. 8 and then there is 1. So we in the morning I showed you the plot in a 2-dimensional, and we said that 3-dimensional also is doable. But here you have to do 9-dimensional plot. Can you do the 9-dimensional plot? So that's first create. So what the basic understanding this morning we learned, it's kind of one of the blockage right here. So that's why the visualization, data visualization is another important topic coming up with respect to data science. So what we have at this point, so far I cannot see really 9 variable at the same time. I don't have the instrument. Okay. So what I can do, you just do pairwise. I'll look at some of the survival time with this one. I'll look at survival time with this one. So it's kind of approximated way, but immediately you have to understand when I am visualizing the data in this way, I'm actually not taking into account what is the interrelationship they have. So I'm losing some information. That means data visualization helps you to understand what kind of parametric model you will be fitting. But if I look at the data in this way, I may make a big mistake. But at this point, I don't have anything else, because that's the thing we have learned in our class textbook. Understand, everybody? So if you guys like, you can find a device where how to visualize 8-dimensional data and what should be the regression surface. All right. So for that, as I said, right now I'm going to use pairwise way, and I can see what kind of relationship is there. Exactly, I'll follow the morning exercise, and I can do that. After doing all sorts of things, I came up with a relationship that with some transformation of the variables needed, which again you can see that I cannot do all this part, but some kind of regression diagnostics, you should learn that regression diagnostic, doing this regression diagnostic, the relationship would look reasonable, at least in terms of the trend, capturing the trend, log of the survival time, that might be linearly related with all these variables. Okay. Sorry, I don't have that plot, otherwise I would have showed you. I might have somewhere, but in the afternoon we can do this part. So what is the idea is that from this plot first, I have to have the idea that what parametric model I'm going to experiment with. Okay, instead of just starting, okay, this. So some plots would help you. So instead of y, so as I said that I have already looked at this plot, you have to take some transformation, then this type of linear model might play. So that means my starting model is going to be log of the response, and then in the predictor variable all of them things would be there. You might say that, well, then model selection is done. But actually not done. The idea is that still I like to go with how many variables I will keep. We already talked about the smaller number of variables would be the better for us, right? It's short for the interpretation. Then later on, if we think that non-parametric regression would have been good, even 1 variables with non-parametric regression would be better. So some kind of variable selections we can do. And this is a classical variable selection technique we might do, or what is called the model selection technique. So there are many different approaches are there. And truly, if you don't do this, so how the way we can do this thing? If you just look at this MAC type of thing, what we talked about, that model uncertainty, but think about how many would be the total number of model. If you have p many variables, total number of possible model is 2 to the power p minus 1, because you can have basically delete 1, add 1, delete 1, add 1. So every one you can think about choice 1 or 0. So 2 to the power p, and the default model is none of them, so that's what you are subtracting 1, 2 to the power p minus 1, right? But here what is the p? P equals to 8, right? 2 to the power 8 minus 1 is how much? 256 or something like that, right? So you have to analyze 250 and all this regression diagnostic you have to play, and then you can decide about a model, which would be too difficult to do. But nevertheless, that's possibly you can do. So what is the idea? Simple way it goes, that you can think about first all models with 1 variables. How many models would be? 8. All models with 2 variables, 8 choose 2. All models with 3 variables, all models with 4 variables, all models with 5 variables. And then fix a criterion. If your objective is still the prediction, probably MAC would be the one. But as a whole package, the MAC, again, as I said, the prediction may be good, but all other things may not be that good. So you should look at some of the other criterions. So there are some of the other criterions well defined in the literature. You can read if you like to know more. I think some of you already know something called the R square. Again, I don't like to go to the details. Typically, I have seen people look at the R square. Everybody understands R square. Even doctors understand the R square, I know. But that can be very measurable, by the way, if you use just the R square in a big data situation. Something called the adjusted R square. Generally, the bigger the value would be, the better. Something called the Mellow's CP. If this value is close to the P, P again is number of like variable 1, 2, 3, as many possibles, the model is better. Some of you heard about AIC, SBC. The smaller the AIC, the better. Smaller the SBC, the better. And press the prediction sum of square. That means you use part of the data for fitting the model, and then remaining part of the data you kind of predicting and look at the prediction error, because you know the truth. The smaller this error, that's the better. So it might happen. So general way, the general principle would be, you first decide what is your target. If your target is the prediction, probably you might look at this 2 and this one lot more importantly, because this is kind of all this dimension. If you like to look at the regression relationship between the variables, then this may not be a good thing, this may not be a good thing. Then maybe this 3 might be the better thing, because these 3 things will try to keep your model as small as possible. Okay? So depending on what is you have in mind, what you like to do, you would like to understand the relationship between the variables, or you like to predict, the criterion varies. But nevertheless, a good model, generally a good model, does a good job for both explaining the relationship as well as for the prediction, if it is a good model. So the idea is that you should consider all these criterions, not a single criterion, and from there you try to understand what could be the best model. Okay? But if you are just very fixed, okay, I am just interested in prediction, nothing else, probably you don't need to look at all this part. You might look at this, and that's why many people look at, R square. R square is very high. But it might give you the good prediction, it may have all other problem. Okay? So, yes.
Basically divided the whole data set into 2 parts, and based on one part I am forming a model, and then I predict with the remaining data points. By doing so, are we not losing, because I am not using the whole data set, what I can immediately see that I should have enough data points so that I can have that liberty.
Yes. Unless you have large number of data points, you are exactly true. So
in case of I have this limited data, which might have been this. So yes, this division or this allocation of this into these 2 groups, how can I do this?
That's usually you should not do that. Then probably you should look at really just given the data set, how well your model fits the data. So generally these 3 criterion tells you how well your model fits the data, and you just believe on that. As I said, that if the your model propagate or mimic the data very well, you expect that prediction also is going to be good. As I said already, if my model really fits the data well, I should be able to actually replicate the data. So that's what, in my personal opinion, you should look at the goodness of fit rather than this or this. Machine learners typically look at this thing, how good the prediction is in terms of splitting the data. But there is no theoretical guarantee. That's the biggest difference between machine learning people and the statistics people. Although your prediction error is small, it doesn't mean that anything. There is no optimality theory, but these criterions, there is some optimal properties are there. You can prove in some sense this is the best models. But this one you cannot prove anything. This is just some measurement. So that makes sense, definitely. You should, given a data set, you should always look for how good this model fits the data. That means given the data, how good your model is. So you don't need to split, actually. But it's an additional thing you do if you have the luxury of having big data. But nowadays we have so many big data, we could do that. But in some cases, it is not doable. Even it's a big data, still it is not doable. Okay? So how the way it generally works. So this is kind of the typical picture. This is the value of the R. Here is the kind of the model size. Model size 1, model size 2. As I said, that if you have the 8 variables, you can have 8 choose 2 different types of model, 8 choose 3 different types of models. As the model size increases, you can see the R square increases. And that's why people, so generally what would happen? You take the larger model, better prediction would be, or because better R square would be. But on the other hand, your model is becoming too big. So in general way, if you follow this thing, if you have say large number of variables, you tend to use all the variables, but then you can end up with a very lousy model, very highly unstable model. Adjusted R square, it's little better because it penalized a little bit for this number of parameters, but it's still pretty much same. Here is this Mellows CP. How the way you can see the plot, basically you look at where exactly it becomes the P. Like for this one, P equal to 3, this is kind of the 3. So that means this is indicating you should select a model with 3 variables. And then all these numbers are there, so probably whatever this model indicates, this model could be the selected. AIC decreasing, then you try to find out where it is stabilized, you can try to find out that model. So this is the way you can see. Ideally, or there is no guarantee that each criterion will end up with a unique model. That means if I apply this, all this thing, it may not end up with a unique model. But you take into consideration all of them and then make a subjective way and do some further diagnostics, come up with a single model which will be used. But the whole exercise is a big exercise for any industry setup. It takes month after month for validation, different types of data, different types of validations, all sorts of things goes on. And then the system build up. So produces the model that perform best with respect to particular criteria. As I said, that if you take a particular criterion, it can produce the best with respect to that criterion. If you take, instead of CP, if you take BIC, it will produce a different model in terms of the BIC. So the idea is that you take several criteria, not a single model, but set of candidate models which perform well. So you take all of them, and total was 256 models, probably come up with 10 models using all these criterions. So you just plot all these things, but note that from 256 to you came down to 10 models. Then it's kind of your lab. You are bringing number of different experimental data, number of different replicates, do some experimentation, and try to find out, pin down from 10 to 5, then 5 to 2. Eventually you might end up with a 1 model. So that's the whole procedure would go on. the candidate model should be further investigated, scrutinized by using residual plots, influence diagnosis, multichromaticity. Also, these are all well established, but it is the practice you have to do, the big exercise you have to do to come up with final model, validate with new data, all sorts of things would go on. Okay? So what's the idea then? Idea is that you use this type of plots from a large number of models, you come up with a small subset of models, say from 256 to even say 56, even if you can come up. That's a big thing. Then from 56 to come down, say 10, then do all these 10, lots of diagnostics, etc., and then you come up with a final model, what should be much more, I think, reasonable in practice. So not really, so textbook is helping you some, but then your practical experience would be the most important thing to do. All right, so if I do this one, let's look at this surgical example. As I said, we'll do this one again in this afternoon. So you have to download that library LIPS, and if you put that command rig subset selection, as I said that already, this one I did already for you guys. See that I'm not fitting on y rather than the log y. And why did I do that? Because I wanted to keep everything under the linear setup, and in a log scale it looks much more linear than the non-log scale. That's why it works. So if I don't do the log scale, you may not get exactly the same result. But note that since all the theory behind is the linear regression theory, so you have to make sure whatever the model you are experimenting with, even if you are applying BIC, you are applying AIC under the linear model setup. So, and when I'm looking the data, it's kind of a transform data. That's what we are looking. So that part you have to do it. Now if I do all these things, then if I run this R, you will see this way. If I am interested in only one variable model, then you choose the X3. If I am interested in two variable model, not the word is not the interested model, rather than the best model with one variable, which is the simplest possible, right? Because our idea is that two things. One is the best model, but the simplest possible best model. Because if your model is too complicated, nobody is going to use it. It would be staying here. So that's what you try to look at, the simplest possible model. That is the simplest one. And if it is the simplest one, you use the X3. What was the X3? I don't even remember. Something blood pressure or something. If you are a little bit more flexible, like two variable model, then you use 2 and 3. Again, I think both of them are blood related. If you can use the 3, then you get 1, 2, X2, X3 and X8. X8 possibly is the gender or smoking, something like that. If you can do for 4 model, then 1, 2, 3, 8. So what this table says, this essentially tells you from the 256 model, the choice it gives you. If I am in like to be simplistic situation, then I have a model already. And then here is all this part is there. So you can go now subjective way. Because whatever the model you will be working on, in reality it costs money. Because people has to work it on, you have to collect the data. Just this data doesn't mean that your model is selected. As I said, that there would be a number of new data set coming in. You have to play with all sorts of things. But generally what you will do, suppose after that, still you are confused which model I will be using. Simplest doesn't mean that always, it's the simple doesn't mean the best. This is the most complicated model. All of them are there. So if I do this one, essentially I am not doing any variable selection. And this makes my life much more complicated, right? So then what you should do, you just start playing with all these 8 models, with all these diagnostics and etc. what we talked about, and try to come up with a recommendation, one of this thing. That could be this one, that could be this one, or between anything. And here the things would work. You do all sorts of things. That means after selecting this one, you again try to find AIC, BIC, CP for this one, for this one, this one, this one, this one, this one. If you have the big model, then a big data set, split the data set, do a training set, do a test set, try to look at what is the prediction error, how it changes, all sorts of things you should see for all these 8 models, and then you come up with a single model.
Sir, before I go for model diagnostic, how do we find this, which variable should I take? For example, for this case 1, I have to choose one single variable.
No, that's what,
How do
with respect to one of the criterions, it has been selected already. So like as I said, that if you are in this case you are targeting something, like your target is the prediction, then probably you put the PRESS criterions is your target. So with respect to that, R already selected this thing. But suppose your objective was the relationship, then you put the CP criterion. Then with the CP criterion, R, you can put that criterion, R will select here. By default, I think it is the AIC. Or generally, it use the AIC to select the model. So what does it mean? That means behind the scene, R actually fitted 8 different model, and then selected this one because the AIC was smallest. Then behind the scene, R actually fitted 8 choose 2 models, and then selected this one with model with y equal to x2 plus x3 because the AIC was smallest here. That's the default one, but you can change your criterion. Okay, that's the way it goes. So the summary was, what the summary, all possible, this is typically called the all possible regression. The all possible regression procedure leads to identification of a small number of subset that are good according to the specific criterion, as I said, that you have to, as a data scientist, given the context, you have to decide what the criterion you are doing. And in this particular one, SBC and PRESS prefer 4 predictor variables, other prefers larger variables. So it clearly different models, given to the different criterion, you will have different numbers, different size of the model. Thus, use the several criterion to find the set of candidate models. Once the best subset is identified, do the residual analysis, all other things already, as I said. So this is called the all possible model selection. And generally this is the classical practice, but you can see that even for a small number of variables, like 8 variables, it can be huge amount of work. But nevertheless, all this criterion what you are using, everything has the theoretical foundation. So what the model you get, we can claim that this model is optimal in this sense. So that's why if you can do this type of thing, you do it. But again, in my experience, as the way we have been talking about the new data sets, etc., you won't have this luxury anymore. But you have to learn this thing how the way it well before you move up. Okay? You have to learn even in a simple situation how to select the model. So this is called the all possible set. Everybody is clear? Now, going little bit moderately complex problem. When you have a large number of covariates, large means again it is not 100, 200, not like that. That was 8, so large means, anybody here has any experience looking the data set with 20 variables even? How many?
I had 127, 28 variables.
How much data?
Cases.
Huh?
For a PhD thesis, 127 variables. So, and number of values I have is 178 managerial data. It's about different aspects of management.
Okay. So 178 and 100 variables.
127.
What did you do? How did you fit the model?
Sir, actually I was working on SPSS.
Yeah, but
Validations and
you can do anything, but how do you know that you really did the right thing? I can see that it was not right without doing anything.
Sample size
150,
and number of covariates.
110 or so, 127.
They are also in by p tends to 1 as well tends to.
It will be very unstable model. Your model, so that's okay. You got the thesis. So I got the thesis probably same way. So don't worry. But probably if I have to do the real job, I don't think that I'll buy your model at all. No way.
But in principle, hard works went through because of the fact that at the end of the day n is greater than p. So all those inverse
theoretically it might go, but it doesn't mean anything. Yes. Also, computer probably it ran, but oftentimes, there are number of I would say that tuning thing in the computer code. If it is close to 0, they kind of make it little bit plus epsilon positive, somehow it is goes through. So in the end of the day, your thing, if I run for a different data set, you might not get the same result or similar result. So in any case, that would be interesting data set if we learn, we're going to the next stage. So, but why you didn't do any model selection? Or you needed all the variable?
Sir, I needed all the variables. Most of the variables, they were clustered into the various subheadings, constructs. So multiple variables under different constructs. So it was a reflexive model. It was supposed to lead to the final outcome. That leads to culture changes and regulatory changes in the organization. So it was multi-stage model. I still haven't submitted it, but I ran a PLS.
Okay.
And it was able to fit.
Yeah, you have to you have to run peer, but okay, that's the, so you know PLS. Okay, you know means at least you run it, but PLS is different. So as you might see, if I get time, I might go to the PLS, but essentially you are doing some dimension reduction over there. So you have to do the dimension reduction. Naturally, it doesn't have the exactly similar meaning of the regression analysis what we are doing. So idea is that if you have so many variables, you cannot do this type of. So bottom line is that yes, you have done the PLS, which is not a really least square regression. How many of you else are do PLS? Stat students? But this is
Penalized
no partial least square.
partial list.
It's one of the important thing, much more chemometrics people does.
But I don't know what is this.
That's the lovely thing. That's the thing that this is very strange to me that why statisticians do not know. PLS is a hot topic, by the way, Shubhro. The theory is pretty much black hole yet, but it works well. And the problem actually came from the chemometrics, not actually she got it from.
Journals, leading journals, and what's the
There are some annals papers are there in PLS, but those papers nobody will use it. The paper which is highly cited, written by the chemometrics people, and it's actually published in chemometrics. That's the interesting.
This is also very well-known journal.
It's very well-known journal, but the paper is written not by the statisticians. That's what I'm trying to say. But then, and the follow-up thing, some of the statisticians tried to give the foundation of that thing. That came into in annals. But the idea came from the non-stat people. So this is also very surprising. Some other people also told me that why don't know the PLS, but in my opinion, PLS should be taught in the standard classical statistics class. So anyway, so that is, by the way, this is not exactly the same list. What we are talking here is a least square regression, but PLS is not a least square regression. It's a principal component regression. So how many of you have done principal component regression? No, that is also.
Principal component regression means in L2 space principal component I can understand, and regression
Yes.
means
So here essentially again in the regression surface, like if you have number of covariates which are highly correlated, you try to find out again few of the principal component, and then regress on the principal component, not on the real variables. So again, these are used by the non-statisticians lot more.
So here dimension is reduced.
Dimension would be reduced, and you are not doing the regression on the real variables.
So matrix
You actually change into a different surface. Then you can recalculate back, but essentially it's kind of one simplest explanation you are transforming.
okay, I'm just telling. Okay, I'm just telling. Suppose y equal to beta naught plus beta 1 x1 plus beta 2 x2 plus epsilon. So in that case, this is the equation of hyperplane, not straight line. Now suppose in some way you can by principal component analysis you can make it that the x1 is your first principal component. So hyperplane is now reduced to the straight line. So that is the principal component analysis principle. That means you are doing the dimension reduction from higher dimensional space to lower dimensional space, and that is some mathematical technique is there. So essentially you have a regression surface, suppose 8 covariates, and now you are taking the first two components. So in that case, based on the first two components, you will reduce to a hyperplane. So that is my understanding.
That is exactly that's the basic idea. And then what the PLS goes in your response also have high number of response same time. So it's kind of
Also multivariate.
yeah, like your multivariate regression you guys did. But once you do the multivariate regression, your number of parameter immediately increase exponentially. So theoretically you can write it down. In practice, it never works. It cannot be, because you can see that how many parameters you are increasing. Suppose you have only one x and two y, and you have only, say, linear model you are fitting y equal to alpha plus beta x, but then you have 2y, then you have 2 alpha, 2 betas, then in the covariance matrix you have 5 other additional parameters. So you are increasing exponentially, and your number of data points could be much less. So naturally your standard least square analysis does not go, or the whatever you have learned in multivariate linear regression, that's in the book, but it is not applicable at all. So the PLS type of technique, so again this is a dimension reduction technique that works well, very well. So okay, so that would be fun. Actually you can, some of the things what I'll do, you can try to apply over there as well. So let's go. So her case, I can see that really a good data set in that sense. So what we are talking about so far, as you already everybody understand, in the stat class we usually talk that all possible subset selection, what we just said, where you have number of variables, maybe 4, 5, 6, 7, that's it. But what if you have large means, say about 30 variables, 30 to 50 in the range of 50, how do you do the variable selection? First thing, if you do the all possible subset selection, 2 to the power 50 minus 1, calculate. You need a calculator, okay? And minimum number of dimension, the reduction would be 1 variable, 2 variable, 50 models, right? And then you have to do all sorts of classical analysis on the 50 models. It's not doable.
2 to the power 50 minus 1.
2 to the power 50 minus 1, then suppose with single criterion, you came to 1 variable model, 2 variable model, 3 variable models, still you have to have 50 models. Then you have to do all this type of diagnostic everything over the 50 models. And judging over the 50 models, it's not doable. Judging over the 10 models, probably still difficult. I think for me, even judging over the 2 model could be difficult, which one I'll take, unless I have a clear mathematical founding. But most in the cases, you have to take some subjective call, looking some different criterions. So looking 50 models, no, you can do that. But there is no theoretical solution. I have to say that there is no theoretical solution. So there are something called the sequential variable selection procedures, which is inbuilt in SAS, SPSS everywhere, because it's very practical. It works very fast and very practical, but no theoretical foundation. In other words, whatever I said just a minute ago, in theory, I can tell you the optimal properties of this model selection. That means the true model selection probability goes to 1, those type of asymptotic is doable. But if I do this type of things, there is no theoretical foundation. Okay? Nevertheless, in practice, we do this part. So what exactly it is? So there are 3 types of sequential procedures. One is the backward elimination, forward selection, stepwise regression. Instead of going to the details, I can just say this way. Backward elimination means you start with the largest possible model, like with all 50 variables models, and then do 1 by 1 by 1 by kind of the F test, or you can do like delete 1 variable at a time, look at what the change in AIC. Look at this, eliminate the second one, see what is the happen in AIC. So 1 by 1 sequentially you are looking, and then see what is the best model after dropping which variables. Then your model becomes 50 to 49, then 49 to 48, 48 to 47. In this way, when you can see with certain tests that you cannot eliminate any further, you stop it. Okay, I'll show you the same example how the way it works.
No, just I'm asking one more thing, since I'm my model.
Yes.
So we have to use the AIC or any criterion we can use?
You can use any criterion. You can do even partial F test. So so let me just go through this backward thing here. Oh, I should have here. Sorry. Probably when I'll start again for this, but idea is like this. So as I said, you start with all variables and then delete say first one, whichever out of the 50, see what is the AIC of that model of the 49th. Then delete second one, still your model is the 49th. So that means you are looking 49 model at the first level and see for which one AIC is the lowest. Keep that one. That means for the model for the one which you deleted, it gives you the lowest AIC, you keep that one. So you become model with 49. Do the same thing out of this. Now out of the 49, you fit 48 models, deleting one by one, and look at where the AIC is smallest. I think it would be good if I show you all these things. Probably in the afternoon I'll do it. And that's the way you go for. Forward selection is completely other way. So you start with 0. There is nothing. Y equal to just constant. That means I'm predicting using the mean. That's a model. Then I'm bringing just 1 out of the 50. I calculate the AIC. Then I'm bringing another one with 1 by 1. That means so I calculate the AIC. So second variable I calculate the AIC. Third one I calculate the AIC. In this way I can calculate 50 AIC, right? Then I look at which one has the lowest value. I included that one. So now my model size becomes 1. Then I'm starting with bringing another one, look at the AIC. Another one, look at the AIC. Out of the 48 models, I look at which has the lowest AIC. So then my model size becomes 2. I do this index way as long as it gives me the lowest AIC other than the intercept model. So then I stopped. So I'll show you this part. That goes to the forward selection. And stepwise selection is that you kind of move forward, backward. So once I have 2 variables in my model, immediately I will try to see if I can reduce one. Because when I'm doing the forward one, then once I selected, I'm not dropping this thing. It is stay in the model. But it might happen that when the third variables come in, I should have dropped one of these previous 2 because they are pretty much related. So that's why stepwise relation is kind of, it's penalizing. Forward is kind of, once it is there, it is in the model. This one is trying to penalize. Once it is get in, next step it is trying to see whether I can drop that one because I am getting a new one. So it's kind of, I am hiring a new employee, then I will see whether I can fire the old one or not. At the beginning I didn't have anybody, I just got somebody. Next I got the new one, let me check whether I can fire this one. That means if the new person can cover up with the old person, I will just fire it. So it's the same principle. Heuristically it is exactly the same principle. So that's the way it goes. And you can change the criterion, as I said, that you can do AIC, you can do BIC, you can do partial F test, you can change this default, but in SAS or everywhere it is, and it is, in my experience, this is the most useful and most practiced model selection criterion everywhere. All the pharmaceutical companies does exactly the same thing to come up with a reasonable model. That means that, so let me first finish in this. So in this way you can come up with a reasonable size model from the 50 to say 10 or 5. Once you come this thing, then do again classical regression, diagnostic, all sorts of things. Because this model, whatever you get, this may or may not have any meaning because this doesn't have any theoretical validation. Because number of multiple testing, etc. going on, so consistency proof we cannot provide. So there is, in statistically, we acknowledge that there is no theoretical foundation, but it just work well. Okay? But once you come down to a reasonable number of models, like a reasonable size of the model, like 4 or 5, then do all kind of classical thing. So then another exercise goes on, and that's the way model selects. So that's why the classical thing is still important, very much important. You cannot just deny this part. So what is the first part I have done? This all possible models. You have to repeat this thing after coming down from here a reasonable number of models. So that's the way it goes. Okay. There are some couple of other procedures.
But these procedures are only valid for linear regression, multiple linear regression or something. I'm just asking.
Yes.
So I didn't see too many papers on the variable selection in non-parametric regression.
No. So the first thing, you will not see any practical way you are fitting non-parametric kernel-based regression on 50 variables.
That's what I'm asking. That,
Okay.
If I can manage 50 to 5, then we'll go for the non-parametric.
No, so you cannot fit that 50 things. So what the way we do, as I said, that you can first transform everything into a linear model. If I get the time, I'll show you how the way we can handle this piece. I gave you already one example. First thing, if it is a non-parametric, how the way you are doing the non-parametric. So basically non-parametric means you have to have some approximation, like you do the kernel density approximation, k nearest neighbor approximation, or I can do the polynomial approximation. Simple example, if I do the polynomial approximation, then this becomes a linear model. No longer it's a non-parametric model, although underlying model is non-parametric, but it's a linear model. Once it's a linear model, then you apply this whole thing. So for one variable, you have one of the polynomial. For the another variable, you have another of the polynomial.
Any non-parametric, any function can be approximated by the polynomial.
By the polynomial, but then you are increasing number of parameters just. Okay. So what would happen? But ideally,
That is a linear model.
that's a linear model, and then you apply all this linear model theory. So if you can build into linear model, whole theory can go well, and that's the way you can do. Okay, that is one thing. But I'm not saying that you have to do polynomial approximation. There is other way as well, and which I might do it if I get the time. But before that, so why model selection is so powerful? I'm showing it in a linear way, but even nonlinear model can be solvable depending on how the way you are solving the nonlinear model. Okay?
So what he is saying, that is clear to everyone?
Yeah.
Because the Bolzano-Weier's stress theorem states that if you have a function on the compact interval, compact set AB, then any function can be approximated by a polynomial arbitrarily good. So whatever the unknown function of whatever the complicated from any function can be approximated by a polynomial in arbitrarily way, less than epsilon. So I will go for in that polynomial that is essentially a linear model. So then I will go for the AI.
Yes. Yes. So that's why understanding the linear model theory is very, very important.
So why
Theory and
telling me
practice.
Right now, I have done so many works on non-parametric regression, so you don't need to do that.
No, still it is you need to, as I said,
My student will write the thesis very soon.
let them do it. Let them do it. That is very nice. So I'll try to show you even some of the highly complicated non-parametric model and how can you use this similar type of techniques of the variable selection. But of course, you have to redevelop the whole theory, and that's not pretty obvious. Okay, because two things happening. Whole thing goes well, but as you see that you are injecting too many parameters, and it might happen your number of parameters can go beyond the number of sample size because of your mathematical artifact. Because we are parameterizing a non-parametric model using additional parameters. Those parameters has no meaning with respect to the data. It has only meaning with respect to the mathematical thing. Okay? So as a result, I won't be able to do exactly the same thing, but similar thing is doable, and that's what we have to learn, how to fit a linear model with less number of data with high number of parameters. That will be coming soon. But so that's why the high dimensional variable selection technique would be important, that it is basically I will be doing non-parametric modeling, but it's a high dimensional thing. And all the parameter doesn't have the information from the data. So we have to deal that part. But bottom line, still you need to know the foundation of the linear model foundation. You have to. So coming back, as I said, This is so the forward selection, backward elimination, stepwise are very good thing. Left and right, it is a heavily practiced procedures, but I cannot publish a paper doing this way because there is no theoretical foundation. But if I go to the industry, I'll do it for sure because that's the most practical way to do. For the theoretical foundation, model consistency, there are two papers you might see: bootstrap model selection, what is called the linear model selection, also by cross validation. Both appeared in, if some of you know what is called JASA, Journal of American Statistical Association, is a top rated stat journal, but you will never ever see anybody anywhere apply this model selection anywhere. So I won't do it. But I have written also a paper on bootstrap model selection. That would also one of my students' thesis, but that's the thesis. But I cannot recommend for the data science people that you do this part. So that's the difference between the statistics people, what we are trying to do, and what is the data science things. But the next part is coming, which would be a lot more useful for the data science purpose. And also we need to develop the theory for that. Theory is not there.
Okay, next afternoon.
No, tomorrow I will do the most of the things.
Since you have discussed something about the variable selection in the linear regression, linear model. So I have something in my mind. I didn't have any note. At least I will try to give an insight that in non-parametric regression how to do the variable selection.
Yes, I think that would be good. I think that would be good.
I'll just try to give some insight. Basically, I'll go through the basics of non-parametric derivation, all those things, but I'll give some idea that methodologically that how one can do that.
Okay. No, that's I think so. So two things we'll do. First thing, it will be good that I'll show you that sequential variable selection before even I move to higher dimensional thing. And then, since we are doing a little bit of non-parametric regression, so you should know more on the non-parametric regression, and at the same time probably he might talk about model selection, non-parametric model selection. Yeah, that should be okay. But interesting thing would be now you guys, so you have also an interesting data. You try to explain, probably do some of these things, or you might even say some of the things what you have been solving, and let's see what the others can say, whether they have the different way of solving this part or not. So that we might do today or maybe tomorrow. But so that is interesting because she has a data set whether we have any solution or not. So the plan would be probably again.
12:15, so we'll come back again to 15.
2:15.
2:15. That was our plan.
2:15. Okay. Okay. Should be fine. All right. Have lunch and then 2:15. We'll have some more on the non-parametric side as well. But you got the idea, right? It has to be very clear that what non-parametric regression does. Now you'll learn. I did this just k nearest neighbor. You'll learn a little bit more. What should be the way it could be doable, and some of the theoretical underpinning as well. All right. And then probably very last moment again I will come back with this data, and then probably she can talk something about her data as well. Pretty good. I think this is pretty successful. All right. So